All right, so let's talk about proving triangles congruent. When we're trying to prove triangles congruent, or at least when we say a triangle is congruent, so let's say we have some triangle pair. Use this as my example. Triangle A, B, C, and triangle D, E, F. What I am saying when I say the triangle A, B, C is congruent to triangle D, E, F, that is me telling you that angle A is congruent to angle D. Angle B is congruent to angle E. Angle C is congruent. Notice how A comes first in this congruent statement, and D comes first, and so those two angles are congruent. Something to keep in mind. Angle C is congruent to angle F. Side AB is congruent to side DE. Side BC is congruent to side EF. And side AC is congruent to side BF. So when I say triangles are congruent, I am saying that every single part of those triangles are exactly the same. Now, that could take a lot of time to prove. So instead, what we have to do if we're trying to prove triangles congruent, instead of showing every single part is the same, there are three pieces that we have to show are the same for any triangles to be proven congruent. Now, depending on what piece you're looking at, which pieces are congruent, you get to choose whether or not that's a valid reason for proof. So up here on the board, I've actually listed all the valid reasons for proof, and I'm going to go through them. So first, if you can prove side, side, side. So this SSS, whenever you see an S, that's talking about a side. If you can prove all your sides are congruent, you don't have to worry about the angles. You know those triangles are congruent. That's one valid reason for proof, side, side, side. But what if you can't prove all the sides are congruent? Well, if you can prove two of the sides are congruent, and the angle in between them, the angle has to be in between them. The angle has to be in between them. Then that is another valid reason for proof. That's called SAS. Okay, what if you can only prove one side congruent? Well, it turns out that whether the side is in between, as is the case here, or if the side is not in between, as is the case here, that's a valid reason for proof. When you have two angles and a side. If the side is in between, then we call it angle side angle. If the side is not in between, we call it angle angle side. Now, remember when I say in between, that means that the side ends and the two angles are bordering that side. As we see right here, these two angles are bordering the side that you've marked congruent. Okay, the final reason for proof is a special case, and it only happens when you have right angles. When you have right angles and the hypotenuse and a leg are congruent, that's a valid reason for proof, hypotenuse leg. Now, remember when I kind of shouted at the computer a little while back, and I said that the angle here had to be in between the sides? Let's talk about why I thought that was important. Because if the angle's not in between the sides, as is the case with this last example, SSA, this is not a sufficient grounds for congruency. It may make two different triangles. So because you can move the two sides that are congruent, because the angle in between them is not marked congruent, you can actually get two different kinds of angles. So this is not a valid form for proof. So if you see SSA, you know that's not your answer. If you write it down, you know you got it wrong. All right, so those are your valid reasons for proof. Again, that's side, 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 when all the angles are congruent. Side, angle, side, when two of the sides are congruent and one of the angles in between them is congruent. Angle, side, angle, when you've got two angles and the side in between them congruent, or angle, angle, side, when you've got two angles and the side not in between them congruent. And hypotenuse, leg, when you've got two sides, one hypotenuse and one leg of a right triangle marked congruent. Those are valid reasons for proving triangles congruent. And if we can do that, we know that every other part is also congruent. Every other corresponding part. Let's go through a couple examples of proof. Let's say I am dealing with this. I've got two triangles here, and I'm given that KM and RC are congruent. I'm going to go ahead and mark those from K to M and R to C. Okay, cool. And from K to M is parallel to R to C. Okay, that's interesting. And I'm trying to prove the triangles are congruent. Okay. So we want to choose the option that best fills in the space. So this is a multiple choice question on your homework, but let's go through and think about this. Okay, so we have restated our given, that's always a first step, and then it says we got some angle is congruent to angle RCJ. Well, RCJ is right here. And it says that that's congruent by the alternate interior angles theorem. So some of you might be thinking, I don't see any alternate interior angles. I would need to remind you what that is. Well, I've got parallel lines here, yes? And I've got a transversal, which means that the alternate interior angle to RCJ is right here. That's angle MKJ. Angle MKJ. That's our alternate interior angle because we've got our two parallel lines and our transversal. Okay, so I know those two angles are congruent and those two sides are congruent. And then it says angles KJM. See, where's KJM? That's right here. Is congruent to CJR. CJR, okay, that's right here. By vertical angles theorem, which makes sense because those are two crossing lines, and lines across from each other and two crossing lines are vertical angles, and they're congruent. Now we have two angles and a side, and is this side in between the two angles? No, it is not. So that's why we have the angle side postulate. Now we've proved those two triangles congruent, which means any other angle pair or sides that are corresponding are also congruent. All right, let's talk about this again. Given BA is congruent to PM. All right, let's go ahead and label that. So BA is right here. That's congruent to PM, which is right here. Cool. And it says KBA. KBA, okay, so that's this angle, is congruent to KPM, which is this angle right here. Okay, so I've got an angle and a side that I've already marked congruent. Now, what are my reasons for this? Well, that was given to us. That space is pretty much always filled with given. Okay, angle K is equal to angle K. That seems like something we should be able to accept. But why do we get to accept that angle K is the same as itself. Well, that's a reflexive property. Hooray for the reflexive property. So now we have two angles and a side, and is the side in between the two angles? No, it is not. So we're using the angle-angle-side postulate. Let's talk about our next proof. We are given that angle JPB is congruent to angle AMB. Okay. And that JA bisects PM. So we know that these two lines here, I'll use a different color, that this is congruent to this, because we know bisect means that we cut in half. We'll probably use that at some point. And we're trying to prove that the triangles are congruent. Okay, so first they copy down their givens. Hooray! And then it says, hey, PB is equal to BM, which is something that I defined up here. I said cut in half. So hey, by the definition of the bisector, we can prove those two things are congruent. Now, that's not enough to prove the triangles are congruent because we need three things. And so far we have sides, one side, and one angle. So then we get PBJ is congruent to MBA. Now, if we look at that, well, two crossing lines cross from each other, vertical angles. So now that we have that, we get to do our final thing where we see that our side is in between our two angles. So we do have angle, side, angle, and we can copy. Now, if you're not sure on what order to put things in, it said prove this. So we can just copy that right down. PBJ is congruent to triangle MBA. All right, let's work another one. So here we're given pairs of parallel lines. We're given that AR is parallel to JB. And we are given that AJ is parallel to RV. Now the reason I'm using two arrows there instead of just one is because I'm keeping a distinction between which parallel lines are parallel to each other, even if it's obvious in this picture, because the non-parallel lines are intersecting each other, still got to do it. All right, so we're trying to prove that VJA and angle ARV, that they're congruent. And notice we're proving angles congruent here, not triangles. By choosing the best option to complete the following proof. All right, so let's go through and see what they did to prove this. So first, they listed the givens, which is fine. That's what you always want to do. Next thing, what they did was they said, hey, that means that angle VAJ and angle RVA, by alternate interior angles theorem, which hopefully you were able to notice, hey, parallel lines, those transversal, those are alternate interior angles. Cool. They're going to use similar logic again right here, where they say VAR, so VAR is right here, and AVJ is right here. And hopefully you're noticing that is also alternate interior angles. So that checks out. AV is congruent to AV. That's the no-dub property. We say, hey, ooh, I want to do this in a different color. Or we know things are equal to themselves because of the reflexive property. That checks out. And so then we say, hey, we've got two angles and the side in between them. That's the angle-side-angle postulate. We've proven the triangles are congruent. Now let's talk about what this statement means. Well, what CPCTC means is corresponding parts of congruent triangles are congruent. So it makes sense why they use a abbreviation here, because that is quite the amount of information to write down. Basically what that means is if you've already proved triangles congruent, like we did right here, then you know what we said at the very beginning, that every single corresponding part is congruent. So if we can prove that VJA, where's VJA? VJA right here, and RVA, sorry, oh, I've made a mistake. VJA and ARV, these are corresponding angles to one another. Then they are congruent because the triangles are congruent, and of course they are corresponding angles to each other. We've already got all the other pairs matched up. So we know we can use corresponding parts of congruent triangles are congruent to prove these two pieces are congruent. BA is congruent to angle ARV. And some of you might be wondering to yourselves, well, how do I know that those are corresponding? Well, those are centered at angles R and J, right? Notice how R and J are both the first letters listed in the congruent statement, which means those correspond to each other because you list them in order of correspondence. So if you prove them congruent, you know they're corresponding. Corresponding parts of congruent triangles are congruent. That's worth another. Okay. So this is talking about this shape PQRS. We're saying it's a quadrilateral. Okay, so quadrilateral just means four-sided thing. With PR and QS as its diagonals. Okay, so diagonals are just these things that are coming and crossing through the middle. Nothing exciting yet. If T is the midpoint of PR and QS, ooh, that is actually useful information. So if it's a midpoint, then it cuts stuff in half, which means that this is congruent to this, and this is congruent to this. Which we're probably going to use here in a minute. Then show that the two triangles are congruent, choose the best options to fill in the blanks. Okay, so first they restate the given that it's midpoint, and because I said, hey, that was given as the midpoint, and thus we knew that they were cut in half. You remember from a recent problem we just did, we get that from the definition of midpoint. The midpoint cuts lines in. Okay, and we know, let's see what angles it's talking about. PTS PTS right here is congruent to RTQ. Well, hopefully you guys are seeing the crossing lines and thinking, hey, crossing lines, this is a vertical angles theorem. And then we have an angle, sorry, a side, an angle, and then a side. The angle is in between. So we can use our side angle side postulate to prove those triangles are congruent. Now let's move on to the next one. So we have two triangles. We are given that QR and QS are congruent. All right, let's mark those. QR, QS. We are given that RT and ST are congruent. Okay. Starting to see something happening here, and we're trying to prove the triangles are congruent. So we'll start off by restating our given that QR is congruent to ST and segment RT is congruent to basically this one. Okay, so we listed it. Hooray! And then the last thing it says is QT is congruent to QT. So QT is congruent to itself. Well, that's the reflexive property. So we've proven all the sides are congruent. So a side, and a side. So the side, side. Postulate. That's how we proved them congruent. Hooray!
We'll begin the staggered transition to third period. Freshmen, you are dismissed.
Sorry about that interruption. Given this last problem, this will be our last problem for this problem. So we're given that ABC and ADC are right triangles. We kind of see that in the picture. And we know that AB and AD are congruent. Okay, cool. Now those are our hypotenuses. Interesting. And it looks like we've also marked AC congruent. So that's given by our diagram. So I can write all this stuff down as given. Now it says I've proven something with the reflexive property. I guess I could say AC is congruent to AC by the reflexive property. That's the only thing equal to itself that's marked up there. So that means I have a hypotenuse and a leg that's marked congruent, which means I can use hypotenuse leg to prove these triangles are congruent. And that concludes our video on proof.